Hello, and welcome to IEEE VTS Young Professional Seminar once again. This is me, your host, Taimur. I'm a VTS Young Professional Liaison, and we have started this series of webinar just to have more interaction between the young professionals and the experienced people sitting in the industry with lots of experience, lots of knowledge. So it's like we get to learn from them. And for that reason, today I have another very interesting speaker and our guest, Giovanni Gerasi. Basically, he is an assistant professor at University of Pompeu Fabra in Barcelona, and he has extensive experience with cellular systems, and nowadays he's more focused on UAVs. So I would not say much about what is UAV, but I would like to just say that uh, since our childhood, we have been fascinated about flying cars and looking into the cartoons. And now we are so close to get this into reality. Maybe like very soon, I mean, we already have drones. We are speaking of flying taxis, and we are speaking of drones that will be doing deliveries for goods. So that means that if we have this kind of let's say transportation system, then it makes sense that they should be communicating with each other for better safety, for better coordination, and lots of other things. I think Giovanni will explain us much better in the coming hour. So before we go there, I would like to request you all that we will be bringing a lot of interesting seminars on this platform. So if you want to just stay up to date, you can just subscribe to this channel, and then you will get to know, because next week we have another interesting speaker. And now I would like to add Giovanni to the stream. Welcome.
Hi, everyone. Hi, Taimur.
Hello. Thank you for taking time. I will not take much of your time, but I would like to hand over the floor to you. And yeah, you are welcome to share the slides.
Sure. Thanks very much. Thanks for the introduction, Taimur. And it's really a pleasure to be here today. And it's an honor. I really like these young professional events by the IEEE. I think they're very useful. And it's a privilege to be participating today. Can you see my screen?
Now, yes, we should be able to see it, and now it is in full. So,
Right.
yeah.
Okay, great. So let's get started because we have limited time, and I would like to leave time at the end for questions, if any. So what's the story with UAV cellular communications? But first of all, I would like to ask, why did I choose this title? So before moving to Barcelona, which is where I live now, I used to work in Ireland for Nokia Bell Labs. And Irish people are really friendly. And what's the story is a typical Irish way of asking, how is it going? What's up, right? So typically, they don't really expect you to tell you any story in practice. It's like a rhetorical question. But today, I will actually try to tell you the story of UAV communications, at least in the cellular community. So let me just introduce myself. So I'm based in Barcelona. I've been moving a lot throughout my life. I could consider myself a world nomad. I've lived maybe in 10 countries, but now I call Barcelona home. The university where I work, UPF, is actually a really nice place to work. And we're currently hiring PhD students or postdocs. So if you are interested or you know anybody who is interested, please send us an email. It would be great to collaborate and work with you. Let me also say thanks to a lot of great colleagues that I had the pleasure to work with. And some of the results I will present today have been jointly generated with them. In particular, I need to mention Adrian from Huawei, Sandeep, Marco, William, Seunjung from NYU, and Angel from UPF here. But many other collaborators also deserve special thanks. So let's get started. The outline of this talk is actually very simple because I'm trying to tell you the story of UAV communication. So the outline is chronological. I'll try to start with what happened in 4G, then move on to 5G, and then, of course, in a speculative way, try to see what's going to happen in 6G for what concerns UAV communications. Well, the importance of UAV communications doesn't really need to be introduced. Taimur already did a great job at saying why we all dream of flying and all the endless possibilities that could be unlocked by having autonomously flying UAVs, right? So here in this slide is just listing some of them, but the possibilities are really endless. And if we want these UAVs to fly autonomously, as Timur said, we would want them to be connected to the network safely and reliably, right? So there's multiple ways of achieving that. We could have a satellite connection to these UAVs. We could have high altitude platforms serving them, and so on and so forth. One of the probably most realistic ways nowadays is through cellular networks, because cellular networks are already there. They are deployed anyway for terrestrial users. So the idea is to support UAVs through terrestrial networks. So here's just some press releases that covered some of my articles with colleagues from Mississippi State University. Basically, the message I want to give here is that UAV cellular communications is a really hot research topic, and I strongly encourage anybody who's interested in collaborating on this topic. So I'm going to go back to the technical stuff now. Take the perspective of an operator or mobile network operator, okay, who considers UAVs or drones as potential users of the network, okay? So there's a pursuit of revenue for the operator. In particular, while nowadays, in many countries, it is forbidden to fly UAVs without a pilot in direct line of sight with them, these restrictions could be lifted in the near future, especially if the technology is able to support autonomously flying UAVs, okay? So the dream of an operator could be to handle this beyond visual line of sight command and control traffic for a UAV. Here, CNC stands for command and control, okay? So this could open new markets and opportunities. Of course, on top of that, there will be also a payload traffic similar to the one we are used to, so data traffic. In the case of UAVs, it will be mostly generated in uplink, as we will mention later, okay? And the dream, of course, would be to do all of this for free for an operator, you know? Basically reuse the existing infrastructure seamlessly to serve not only terrestrial users, but also UAVs. But the reality is that it's not that easy. There's no free lunch. So the operator must somehow prepare the ground to accommodate aerial users. So there's another side of the coin, which is seeing UAVs as base stations. So instead of seeing what the network can do for drones, we can see what drones can do for the network. Okay, so another dream for operators is using UAVs as mobile base stations, you know, dynamically repositioning them on demand when there's a sudden capacity need increase or there's some disaster situation, the network infrastructure is down, you name it, okay? So this one you see on the right of the slide is actually a prototype that was, well, the first sketch of the prototype developed by Nokia Bell Labs when I was still working there. So the reality is that this is not as easy. Again, you need to identify optimal locations to place these drone base stations. They, of course, have limited flying times and there are strict regulations, okay? And you need to provide a wireless backhaul ultimately, okay? So if a UAV has to be used as a radio access node, you still need a backhaul link from the ground to the UAV. So this is the reason why, in my opinion, the link from a ground base station to a UAV is the most important one. It's the one to take care of because it's the key to unlock all these different use cases. And that's what the 3GPP started focusing on. So I'm going to start giving a very quick summary of what happened, starting with 4G LTE support for aerial vehicles. Okay, so the work in the 3GPP started about in 2017, almost 4 years ago. Okay, there was a study item definition. Okay, so companies studied the use cases, the requirements, channel modeling, and possible technical problems. Okay, I'll say more later. And then once this was concluded, a work item started. And then the work item was concluded with actual improvements to be made into the standard to support aerial vehicles, okay? But this doesn't stop, of course, as the 3GPP evolves through future releases, the work continues, okay? With new use cases, new requirements, and new technical solutions to be found. So the first thing that the TGPP did was identifying some traffic requirements. Okay, we need to know what the requirements are before we can even answer the question, is this feasible? What else do we need, right? So there are two main types of traffic, as I already mentioned before. The one that is really important for UAV is the command and control link, command and control traffic. This is both in uplink and downlink. okay? So that is necessary to have autonomously flying UAVs. The throughput requirement for this link is not very high. It's between 60 and 100 kilobits per second, but it needs to be reliable and with bounded latency, okay? And then there's an application data traffic, which is the one we're used to, except that for the case of UAV, it's mostly in uplink. It's expected to be mostly in uplink because lots of UAVs do video streaming, right? So mostly in uplink. Right. Then to see what happens to simulate the behavior of the network when we try to integrate UAVs, we need a good channel model, right? So the traditional channel modeling that was available a couple of years back was the 38901, okay? But this was not calibrated for aerial uses, okay? So there was a study by the TGPP to basically upgrade this channel model through measurements run by many key industry players, okay? And then a new channel model was defined that depends on the height of transmitter and receiver. So all the parameters in the channel model, so path loss, probability of line of sight, the fast fading, shadow fading, everything depends on the transmitter and receiver height. Okay, so this channel was generalized for the case of UAV users. Okay, then the TGPP also defined for the studies how fast these UAVs would move, at what height they would be, and they would be between 0 and 300 meters for most cases of interest. So then the study began, and some challenges were identified. Okay, so what was so special about UAV? So now we're really getting into the core of the matter. UAVs fly high. Okay, so obviously they are likely to be above the clutter of buildings in a certain city. That means that they experience a lot of line of sight links with many base stations. Okay, they have a bird's view, which is good in a way but bad in another. Because, for example, in uplink, they can generate harmful interference to many ground users. And because their link is line of sight, the interference they create can be overwhelming for ground users. In downlink, they turn from offenders to victims because they see many base stations and they receive interference from many ground base stations. So there's a problem in downlink as well. And regarding mobility, mobility is really challenging, as I will explain better later, because UAVs see many base stations. They only see the upper part of the base station. So typically a base station is down tilted and it has a main lobe facing to the ground, okay, to create a cell for a ground user. UAVs don't see that because they're high. They see a bunch of secondary lobes. So they see very sharp and sudden fluctuations of the signal strength. So as they move, the preferred base station can change very, very often. So this is really challenging for mobility. I will say a little bit more later. Cool. So here's exactly what I was talking about regarding cell selection and association and mobility. Okay. Before we go into the details, how does cell selection work? We go around our city with our mobile phone. Our mobile phone will select the base station that provides the strongest signal. Okay. Typically, this is the closest one, not necessarily, but typically it's the closest one. So imagine that we are on the ground. So this drone could be just a mobile phone, okay, on the ground. The drone will never be so close to the base station, or the user will never be so close. It will be around here, let's say. So it will be illuminated by a main lobe, okay? So here, this figure on the right shows you the antenna gain seen by the user as the 2D distance increases, basically as the user moves away, okay, towards the right. So when the user is at 1.5 meter, this is the trend for the antenna gain. It's like a smooth variation. Okay, as it goes away, it goes down, but it's like sensible. It's something that we would expect because it still stays in the main lobe. However, when you are up high, for example, at 50 meters, okay, we look at the antenna gain. The antenna gain has a lot of peaks and notches. Okay, there's a lot of very sharp fluctuations. That's because this UAV is higher than the base station. It will never see the main lobe. It will just transit from one secondary lobe to another. Okay. So you see, this is really different than what happens to ground users. That's because the base station was dimensioned for ground users, not for UAVs. Now I'm going to show you the same thing from a different angle, perhaps to try to clarify it, okay? Here I show you the distribution of the distance between a certain UAV and the serving base station. So the base station that best provides service for the UAV, the strongest signal. When the UAV is on the ground, this distribution is pretty smooth, and the serving cell is somewhere between 50 meters and 500 meters, let's say. Okay, so something reasonable. But when the drone is high, let's say here at 150 meters, look at the weird shape of this CDF. We can observe two things. First of all, this staircase behavior, and those steps correspond actually to the secondary lobes of the antenna pattern that I showed before. And second, we see that these distances are considerably larger. So in general, drones that are high tend to associate to base stations that are further away. Here they associate to base stations that are far away. Now you switch, take the perspective of the base station now. Here we took the perspective of the drone. Now take the perspective of the base station. Put yourself here in the middle of a cell, okay, and see where the drones that are associated to you are located. So these red dots are all drones associated to this cell in the middle. And you see that there's a clear pattern. They form these circles that are discontinuous, and each of these regions correspond again to one of the side lobes of the base station. Okay, in this case, the drone is at 150 meters. So this is basically, in a nutshell, is to show you that cell association works very differently when you're up in the sky. Network was not prepared for that, so there are technical issues to be addressed. And of course, as the drone moves, it will go from one region into another one, and it will change the preferred base station. That means the drone will have to perform a handover. Okay, cool. Now let's go. Let's move on to the problem of interference that I mentioned. Remember, I told you interference is a big deal for UAVs. So here I'm showing you the performance of UAVs in downlink. Okay, the network is fully loaded in this case. It means every base station has traffic. So here I show you the SINR for a UAV on a physical resource block, which means on a time frequency resource, as a function of the height of the UAV. So the higher the UAV goes, let's look at the black curves, just for simplicity, they represent the SINR, okay? So you see the SINR goes down. The higher the UAV, the more the interference is overwhelming because the UAV starts seeing more and more cells interfering. And so the SINR goes down. And it goes below this blue line, which is the minimum SINR for modulation coding scheme that is non-zero, right? There are three curves here. They represent the 5% best, the median, or the average, sorry, and the 5% worst SINR. So things get pretty nasty, at least in the case of a fully loaded network. So definitely UAVs, in this case, cannot achieve their target rate for autonomous for command and control, which was 100 kilobits per second. Right. So given these problems, some solutions were standardized, at least in LTEA. Okay, I'm going to overview 5 of them, the 5 items that I believe could be the most interesting for our research community. Okay, so first of all, uplink power control. So you know, power control is really important in cellular networks because it's pretty much like when you're using a microphone. If you are close to the microphone, you lower your voice. And if you're further away from the microphone, you raise your voice. Okay, so it's the same thing for a user. The closer it is to a base station, or the better the channel conditions are, the lower the power it transmits. Okay, so this is done through what's called fractional power control. Okay, because you compensate for the path loss partially. That's why it's called fraction. Okay. So typically this is done with 2 parameters, and these parameters, alpha, which is a path loss compensation factor, and P0, which is a range extension parameter, were adjusted for UAV users because they have different propagation conditions. Then some new signaling was introduced, okay, for a UAV to basically communicate its height to the base station, and also for a UAV to communicate interference. So if the UAV sees that it's receiving strong signals from many base stations, okay, strong reference signals, then it can tell the associated cell that there's a problem, and so maybe the network can take some countermeasures. Then 2 more items. One is about subscription-based access. So in general, not all UAVs in the network should be authorized to fly high and receive service, okay, unless there's a service agreement. So some signaling was introduced for that as well, such that the network knows which UAV is authorized and which one's not. And then, of course, regarding mobility, new signaling was introduced such that a base station might know in advance where the UAV is going in order to predict which other base station to offload the UAV to, basically anticipating the handover, making it more efficient. Right, here are some references in case you're interested in the technical documents from which I have listed out these contents. And now let's move on because the 2GPP hasn't stopped, of course. So new US use cases and requirements were identified for 5G new radio. And here I'm just going to summarize all the discussion. Basically, I would like to group all these studies into two categories. One has to do with enhancements for UAVs, okay? So new service level requirements, new KPIs for new applications, okay? So always more and more demanding, of course. And also some studies for remote identification of UAVs. This is for traffic management authorities because it's really important to determine the identity of a UAV and its controller, okay? So there are several use cases, and this in particular one 2GPP document that I like that lists at least 10 new use cases for UAVs. Here I have listed some of them. And of course, they include high resolution video live broadcasting. Now, for the first time, radio access through UAV, which means UAV used as a relay or as a G node B, as a base station, okay? Autonomous UAVs controlled by artificial intelligence, and so on. So obviously, the requirements for all these use cases are extremely diverse. Because depending on the applications, you might need high throughput or low latency or reliability or positioning, etc. But in general, I can say in summary that there's up to 120 megabits per second required per UAV at the application data layer, and with 20 millisecond latency. And also reliability has to be really high for the command and control signal. Okay, so high speeds, of course, have to be supported, and also positioning, and so on and so forth. So here's some references on those two documents. And now, once we have identified, let's say, new use cases, more and more demanding, I will move on and touch upon two 5G new radio technologies that can be possibly enablers for all these use cases that can meet the new expectations we have from the network to support UAVs. Okay, I will start with Massive MIMO, which I believe most of us are familiar with. So to show how Massive MIMO can help supporting UAV users, I will compare different scenarios, okay? 4 scenarios. Let me start with a baseline scenario, which is what I call a single user mode, okay? So in this case, there is no Massive MIMO. This is a conventional deployment. Each base station has 3 sectors, tries to serve ground users and also UAVs, okay? There is no spatial multiplexing, nothing like that. So each cell has an 8x1 array, but only one radio frequency chain, okay? So only one user can be multiplexed on each physical resource block, no Massive MIMO. Then the second scenario is what I call Massive MIMO. And in this case, base stations have big arrays, 8x8 with cross poles, so 128 radio frequency chains. In this case, they can spatially multiplex several users on each frequency. You see, they can point beams. So by pointing beams, you can multiplex users at the same time on the same frequency, okay? For this, they use zero forcing, okay? And they need to acquire channel state information. This is really important. What do I mean by that? So when you want to point a beam to a user, you need to know where the user is, okay? So you need channel state information for that user. So the way this is done typically is in a TDD way, time division duplexing. So because of channel reciprocity, the user sends a pilot, the base station estimates the channel, and then points the beam, okay? And these pilots are reused. So as I will explain later, there's a phenomenon called pilot contamination, okay? Because there's interference in the channel estimation phase. Right, so we will see that Massive MIMO is going to bring huge advantages compared to the previous scenario, but still there's room for improvement. And that is why I introduce some upgrades to do even better than that. So now what about also UAVs have some antenna arrays, smaller ones, of course, but if UAVs have antenna arrays, they can steer their beam towards the serving cell. So that could be really good because they can amplify the signal they receive, and also they can filter out interference, okay? So in this case, we assume we call it AA UAV, adaptive array UAV, okay, that they can perform beam steering. And finally, the fourth scenario I'll consider is the one I call Massive MIMO with nulls. So this upgrade is on the network side. So now, given that I have a Massive MIMO base station, not just I can point beams, but I can also leverage my spatial degrees of freedom to suppress interference. So this is what I represent here. A null is basically a radiation null. It means I suppress the signal on a specific direction and also in reception, right? So if I know that there's a neighboring user associated to another cell who could be interfered by me, I make sure I suppress whatever that user receives. And I do that in data transmission phase and also in the channel estimation phase. We will see that this brings huge advantages if done properly. So right, so now I'm going to show you performance. In this case, let me, right. So this is the downlink for MSIMIMO, okay? And I'm going to show you a distribution of the rate in megabits per second for ground users shown in black and for UAVs shown in red. So we have both types of users coexisting, okay, in the network. There are two lines for each case. One is with perfect channel state information, solid, and the other one is with realistic channel state information acquisition with errors because of pilot contamination. And this is in dashed. Let me just quickly explain for those who are not familiar with this, why is there imperfect channel state information acquisition? Because as I told you, users send their pilot signals, okay? And these pilots are some sequences of finite length. So they need to be reused at some point, 1 kilometer away, 2 kilometers away, right? So whenever another user is reusing the same pilot, it creates ambiguity, okay? It creates some interference. So the channel is not perfectly estimated. That's why you see there's a gap in performance when channel estimation is not perfect. This gap is actually quite significant. It's like 50% of the median, as you can see, okay? So what do we observe? First of all, the good news. The good news is that compared to the plot I showed you previously with no massive MIMO, you remember those SINRs were really terrible. In this case, everything is largely improved. The rates are pretty good. They're well above the target of 100 kilobits per second, and that's for three reasons. First, because the SINR is boosted thanks to the beamforming gain. Now, massive MIMO does beamforming. Second, because when everybody does beamforming, they focus their energy towards their respective users. So your neighboring cells are going to beamform to their users, and their users are mostly on the ground, so they point down. So a UAV in the sky benefits because it receives less interference. So once again, beamforming gain and less interference. Plus, of course, there's a spatial multiplexing gain because when you multiplex multiple users on one time frequency resource, then you get a linear scaling capacity. So long story short, things get so much better compared to single user setup. But we see that still there's a gap caused by pilot contamination. And you see this in downlink. Notice that this is in downlink. And before I told you that in downlink, who suffers from interference is the UAVs. It's not the ground users. But in this case, the ground users suffer because their channel is estimated in the uplink. And in the uplink, they are strongly interfered by UAVs. And then this poor channel estimation has an effect on the downlink throughput. So you lose also the downlink. So after all of this, I would just say to summarize that massive MIMO is great, but massive MIMO alone might not be enough if the network is fully loaded in a strong interference setting. So now we move on to see whether all those upgrades in the network can help somehow. So here again, I show you the downlink of a UAV, and this is the percentage of UAVs that have a rate above 100 kilobits per second. Basically, I have this requirement of 100 kilobits per second for the command and control link. So I'm gonna check how many of the UAVs meet this requirement. And I try this for different heights of drones, 15, 75, 150, and 300 meters, and for different schemes, okay? So for different scenarios, right? The first observation we make is that the performance goes down as the UAV goes up, right? For all the schemes. That's because we know that the higher the UAV, the more the interference. So the scenario is more challenging. However, we see that some schemes are much more resilient to this interference, and the single user schemes are not. You see that once the UAV is high, interference becomes overwhelming. But massive MIMO, particularly with the upgrades, multiple antennas at the drones, or interference suppression capability at the base station, can do much, much better. In particular, the scheme in yellow, massive MIMO with interference suppression nulls, seems to be the one providing the largest gains and reliability. Here's some references on basically what I've been talking about now, in case you want to dig deeper. And if you're interested in what I talked about so far in the talk, well, then I recommend this book that we have just published with Wiley, which contains these topics and of course, much, much more. We co-edited with some leading experts in the field. Now let's move on to another key 5G new radio technology, of course, millimeter wave. What else? That could potentially help us boosting the capacity link to UAVs. So the dream, once again, for an operator is to use the large bandwidths available at millimeter wave frequencies. This is one of the reasons why millimeter wave is now part of 5G. And also because millimeter wave works very well in line of sight, UAVs are very suitable for that because since they're high, potentially they have a lot of line of sight links to the serving base station, okay? And of course, the dream obviously is to do this for cheap. So reuse the 5G millimeter wave infrastructure that is being currently rolled out anyway, okay, to also serve UAV users. So that's the dream, okay? You have these millimeter wave base stations and you want to serve also UAVs. Well, the reality is not that easy as always, because one should actually evaluate really the coverage and the rates in urban areas because there are possible blockages even for UAVs, right? So the question is a conventional millimeter wave deployment sufficient also to serve UAVs? Do we need to deploy extra base stations here? In this figure, I have put some extra base stations on the rooftop dedicated to UAVs. So this is a very important question in my opinion. And in all of this, to be able to answer the question, we need good models. And currently, the standard defined model doesn't seem to be calibrated at millimeter wave frequencies. So that is why, together with some colleagues from NYU and other institutions, we have first of all proposed a new channel modeling for millimeter wave UAV communications, okay, which is publicly available, okay. So how this modeling works, we have a two-stage generative neural network. So it's a machine learning approach. We train the neural network with ray tracing data. So we generate ray tracing data for links of this type, terrestrial base station to UAV, base station on a rooftop to UAV, etc. Okay, and we generate this through REMCOM's ray tracing wireless insight tool. Okay, then we train the network, and once the network is trained, the network is able to generate a statistical channel model for us, producing the line of sight condition probability, the path loss, the delay, and all the angles of departure and arrival. Okay, for all of this, we considered two types of base stations. Base stations on the street level, which basically are like the typical millimeter wave base stations, and also rooftop mounted base stations to see if they can give us more in the case of serving a UAV. Okay, of course, other types of base stations are not precluded. The ray tracer can generate those data, or you can input measurements to the model as well. Here, I'm just going to go briefly over the two-stage generative neural network to explain the framework. So there are two stages, as the name suggests. The first stage produces the link state. Basically, the first stage tells you if the link is in line of sight or no line of sight with a certain probability, okay? What inputs does it take? U, which is basically a vector that contains the distance between the base station and the UAV, okay? And C, which is like the cell type. In this case, there's only two types, street level base station or rooftop mounted base station, but this can be generalized, okay? That once the first stage produces the link state, this is fed into the second one, the second stage, which takes again, of course, the same inputs, so the distance and the type of base station, and in this case produces all the parameters, the path loss, the delay of each path, the angles of departure or arrival, both in azimuth and elevation. And therefore, from these, you can calculate SNRs, SINRs, and the likes, okay? So again, we needed to train this network. Ideally, we would have done it through measurements, but measurements are not easily available for millimeter wave UAV comms. So we used a tool from REMCOM. So we use ray tracing data at 28 gigahertz. For that, we took 4 cities as an example. Okay, so the actual building configuration of these 4 cities, Tokyo, Beijing, London, and Moscow. Why did we do that? Well, we thought they were representative of urban environments, and they're also not the same. They exhibit some differences. Now, I will say more about that. As you can see, in Tokyo and Beijing, there are higher buildings in general, and in London and Moscow, they are a bit lower rise, okay? And these buildings are always interleaved with patches of green. That's because we took the city center, but one could take absolutely anything. Okay, the framework is general. For these cities, we deployed UAVs at different heights, 30, 60, 90, and 120 meters. And we deployed terrestrial base stations on the street level and aerial base stations on the rooftops, about 30 meters, let's say, okay? Right. So once we train the model, here I'm going to show you some very significant parameters for the channel model. I will start with the probability of line of sight, which is critical, as we know, for the link budget, for the interference, etc. So we have two different cases, Tokyo, Beijing, and London, Moscow. We have paired these cities into environments. So if you're familiar with the 2GPP, this is actually commonplace. The GPP defines urban macro, urban micro, suburban, rural, etc. And the same is done for other bodies. ITU does the same. Okay, dense urban and less dense urban, and so on. So here we did our study by putting together Tokyo and Beijing because they were kind of similar, but this can be generalized. Basically, you can have any grouping of cities, and I will show you actually how the model captures this environment. Okay, I will show that later. So let's move on to the probability of line of sight. What can we observe? So first of all, we have the data and the model. And the model matches the data pretty well, okay, in both cases. That means the neural network was trained properly. What about technical considerations that we can make? Well, we see that with elevation, so the higher the UAV, the higher the probability of line of sight. Okay, the higher the UAV, the higher probability of line of sight. This makes sense. And also, the further away the UAV horizontally, the lower the probability of line of sight. So this makes sense. Also, we see that for terrestrial base stations, the ones on the ground, the probability of line of sight is lower. This makes sense because they're often blocked by buildings. For aerial cells, there's line of sight for higher UAVs and for UAVs that are further away. Okay, the same for London and Moscow, except that in this case, in general, overall, the probability of line of sight is higher. That's because there are in general lower buildings. So this kind of makes sense. Now let's move on to path loss generation. Okay, so how do you calculate path loss? You receive several rays, and then you have an antenna pattern. You basically weigh all these rays with different phases and different antenna gain. So for simplicity, in this case, we consider omnidirectional antenna pattern just for illustrative purposes. Okay. So what did we show here? Okay, I'm going to show two things. Some intra-environment evaluation and some inter-environment evaluation. I will explain what that means. Let's start with the intra-environment. So here, we take the data from Tokyo and Beijing, we train the network, and we see what the model produces for the path loss. And there's a match, okay? So it matches very well. Also, there's a dual slope path loss shown here, which basically is due to the line of sight, non-line of sight transition. So the model captures this very well, right? Then we did some inter-environment evaluation. This is a little bit tricky. What did we try here? We tried to train the network, the neural network, on data from Tokyo, Beijing, and see if it produces, if the model can produce accurate channel parameters for London, Moscow. So basically, we want to see between different environments how this can be generalized. Okay, we did this test, and what we see is that for terrestrial cells, meaning cells that are on the street level, there's match. Basically, they all behave the same way, at least in terms of path loss, but not for aerial cells. Okay, what does this mean? It means that when we look at this London-Moscow model, when we compare the path loss for London-Moscow, this is different than the path loss for Tokyo-Beijing, okay? And so we ask ourselves, why is that? Where is the difference? And the difference is in the line of sight, non-line of sight link state generation. So to verify that, we fed the London-Moscow neural network with the actual link state instead of generating it with the neural network, so line of sight or no line of sight, and then we generated all the other parameters. And in that case, there was a perfect match. So long story short, we show that most things can be generalized across different cities, but there are other features that inherently are specific And in this case, it's the probability of line of sight. That obviously depends on the building's height of a certain city. So in the case of London, Moscow, the probability of line of sight was being overestimated, okay, because there are lower rise buildings compared to Tokyo and Beijing. Right, let me move on for the sake of time to angle distribution. Of course, this is a very important parameter, right? The angular spread in millimeter wave communications. So here, some key messages. First, that again, for both environments, data and model match very well, okay? Here you have the angle of departure in azimuth and elevation, and the angle of arrival in azimuth and elevation. They match pretty well, okay? Also, you see that as you increase the distance, so as base stations and UAVs get further apart, there is less local scattering, so there's less angular spread. This makes sense as well in practice. What else? I could say that there's also greater scattering at the base station side, which is the angle of arrival, because we consider transmission from the UAV to the base station. So the angle of arrival is at the base station side, and there is more scattering. That's because the UAV usually is elevated. It doesn't have buildings nearby, but the base station does. So there's more scattering next to the base station. And to conclude, just let's show the SNRs, and then we make some considerations on this. So this figure shows the median SNR for aerial and terrestrial cells. We see that aerial cells provide good coverage, even at large horizontal distances, okay, especially if the drone is high. So good coverage. Terrestrial cells don't do as well, but surprisingly, and here I'm going to say a little bit more, they provide good coverage at small horizontal distances, even when the drone is high. Okay, so how is that possible? The drone is very high, and still the terrestrial cell provides good coverage. So remember that these millimeter wave cells are down tilted because they are designed for the ground. And there's a very strong back to front gain, meaning that on the main lobe, between the main lobe and the back, there's like 30 dB difference in terms of antenna gain, but still they can cover up. So why is that? We further investigated that. So this is not due to the direct vertical paths only, because the base station is down tilted, but it's rather due to some scattering. Basically, the ray goes to a building, and then it goes up and catches the UAV. I will explain this a little bit better with an illustration. Okay, so pictures worth 1,000 words. So here, let me illustrate this. We have two scenarios, okay? Red with a base station on the ground, blue with a base station on a rooftop, okay? And there's a UAV here at 120 meters, 120 meters. So the coordinates are 120 and 120 in elevation, okay? Here I show you the CDF of the SNR seen by the UAV. So in the two cases, red for the red setup and blue for the blue setup. So what can I observe? Well, first of all, for those who are not familiar with this, there is a knee in these curves. What does it mean? It's the transition from non-line of sight regime to line of sight regime. In the line of sight regime, the SNR is much better, obviously, than in the non-line of sight. So what do we observe between rooftop cells in blue and ground cells in red? That the rooftop, the aerial base station, have a better antenna gain. So see, there's a gap of about 10 dB here. Why is that? Because in this case, they had 3 sectors and they're up tilted. So they have a better antenna gain. The terrestrial ones are down tilted. So that's why the gap. Then we observe that the probability of line of sight, which is the fraction of use of UAVs in line of sight, is also higher with aerial cells. Okay. Of course, they are elevated. They tend to have less obstruction. And so how do you see this probability? You see this knee, it occurs at 0.15. It means that 15% are in non-line of sight, 85% are in line of sight. For the red case, only 60% are in line of sight. So this totally makes sense. And now, let me show you one more thing. Now let's put the drone right on top of the base station. Okay, so now my X coordinate is 0, and the Z coordinate is 120. So now, of course, everything is in line of sight because the drone is always on top of the base station. So you see 100% probability of line of sight. Once again, the blue case has a better line of sight path, about 25 dB gain. That's because it's up tilted. The terrestrial cell is down tilted, okay? But there's a very interesting phenomenon here. All these points here, they correspond to non-line of sight paths that add up on the line of sight path, okay? So this spike is the line of sight path between a terrestrial cell and the drone. And then there are some ground reflections or reflections from buildings, for example, like that, bang, bang, okay, that sum up sometimes constructively to the line of sight path, and they can actually increase the total SNR by a large margin. In some minority of cases, can even outperform the up-tilted area base station. So this is a very interesting phenomenon that we observed, which tells us that maybe millimeter wave networks are actually in a good position to serve UAVs, because even in spite of this down tilt, there could be good reflections that catch the UAV at some point. Right. So just to conclude, the way forward on this is that we produces this channel modeling framework, and the ultimate objective is to train it with measurements. Okay. So this is publicly available. So if any of you want to use the data set or the model itself, or if you have measurements and you want to train the model with measurements, you're very welcome to do so. I have a reference later. And we are continuing our deployment studies, because in the end, we want to see what the capacity is. So for that, we need to measure also interference. And we want to quantify the benefits of having rooftop mounted base stations. So if this does provide a gain, how should we design the sector? You know, how many sectors, what the up tilt should be, and that depends on the intersite distance, so the density of these, the height of the drone, and many other parameters. So here's some references. As I mentioned, here is the repository on GitHub for the model, and here's some papers where you can find the technical details. And now let me just conclude with a look at the future. So what's going to happen in 2030, about 10 years from now? What should we expect for 6G and for our society in 10 years' time? So this is, of course, speculative, and I'll be glad to have any inputs from you if you have any different ideas. I think that the use cases for drones can only keep increasing. I would expect the same use cases as I mentioned already, but with more drones as they start proliferating. Also, more use cases with drone access nodes, but also new disruptive use cases. So here, what I have in mind is flying cars, okay, advanced urban mobility, aerial highways, cargo drones that deliver packages of any kind. You're probably familiar with Amazon Prime Air, which is a project for delivery with drones, okay? And all these use cases are going to require higher requirements, right? They're going to need high data rates, for example, because to have low latency, you might want to send uncompressed video, and therefore you need a super high capacity. You need to be ultra reliable and super connected to be able to have advanced urban mobility. There's about 100 cities in the world currently working on advanced urban air mobility. So it's really coming. So what technologies can support this? Here again, on a speculative way, I try to list some technologies that I think could actually play a role. And if anybody is working on these technologies, I encourage them to also consider UAVs as a potential use case to support. So I'll start with non-terrestrial and satellite communications. I think this is coming. The 2GPP is working on non-terrestrial networks very actively. The satellite industry is launching satellites. There seems to be a convergence with the 3GPP. So this could be very good for providing backhaul for UAVs, for example. If you use a special UAV as a radio access node, the backhaul link could come from a satellite. It's just an example. Cell-free architectures could also be instrumental, because with a cell-free architecture, you turn interference into useful signal. So you could relieve interference and also have some macro diversity for more reliability. Reconfigurable intelligent surfaces, again, is a super hot topic. The question is, can the wireless environment maybe follow the UAV? Because conventional base stations, again, are down tilted. They are not meant for UAVs. What about a smart environment that can somehow compensate for that and follow the UAV and provide always good signal, okay? And terahertz communication. Of course, there are very high challenges there, but the potential to provide a super high capacity link point to point is there. And of course, the challenges are mobility, wobbling, and it's difficult to align the signal. But there's a high potential for high capacity backhaul. And in all of this, AI could be seen as a tool, of course. Channel models become more and more complicated as we start having users at different heights with different mobility patterns and features. So it could be that AI could be a tool for the channel modeling of the future, and also for optimizing the network, managing mobility, and who knows what else. So it's been a great pleasure to give you a brief story of UAV cellular communications, and I hope you enjoyed the talk, and I'm here if you have any questions. It will be a pleasure to take them.
Hello. Yes. Do you hear me?
Yes.
Great. First of all, thank you very much for this wonderful presentation and explaining things very clearly and in depth. And for the last part where you offer to share the material and yeah, also the models that you have worked with, I think that's really good, especially for the PhD students. So while you were speaking, we had some comments and questions. For instance, yeah, this is amazing. Thank you for sharing. Thanks for sharing this. So it's acknowledgement. Yes, we had something good. And in the beginning, you had this how realistic and feasible it would be to have a UAV as a base station. Uh, I think you explained this in the beginning.
I can briefly comment on that. Like, I think this is a really good question, and it's actually what I asked myself when I started working on UAV communications. I saw a trend you might be aware of. The industry was mostly looking at UAV as users, and academia was looking at UAVs as base stations. So I was in the industry at that time, so of course I care more about UAV as users. In general, I saw it more far-fetched, because really I believe these UAVs would still need a backhaul link, which could be problematic. But now there's a new line of research which is about tethered drones. I don't know if some of you are familiar with that. So basically, it's a drone that flies, but it has somehow a cable attached to it. So this at least solves the problem of power consumption, because at least it's supplied with power. In some cases, it can be also supplied with backhaul, so with the data link. This could be an interesting, there's some groups that are working on that I'm aware of, and there's also companies that are started looking into providing that service. So that could be actually the trade-off that could make it more feasible. I don't know if that answers the question, but
No, I think that's right. My understanding is that power is one of the main concern when we speak of the base station. So if there is a cable, then it may solve the problem. Yes. And with that, I think there was another question that I posted here, just so I don't forget that. It's about the stability, because we spoke of millimeter wave, and then the beam alignment is one of the key aspects. And if we have a drone that is not stable, and let's say we speak of the cable, then how would it would impact the stability, impact on the link reliability, and then the sensitivity?
this is a really good question as well. In our study, we are not there yet into study mobility issues. We are at the stage between um, coverage and capacity studies, but this is really important. I tend to be optimistic because I think whatever is being standardized for 5G should support mobility up to a certain extent. So as long as these UAVs do not fly too fast, then whatever is designed for terrestrial uses might work. Plus, if they do have line of sight links, I suppose this eases, in a way, the beam alignment process. And could you do better? Well, yes, maybe as in the case of mobility, if you have information on the trajectory, then you could exploit this to follow the UAV with a beam. That could be some intelligent solution for that. And ultimately, I think you still might need a sub 6 gigahertz coverage umbrella just as a fallback. You might not want to lose connection.
Agreed.
What do you think?
Yeah, no, I think that is correct. but it's still, since it is the things that are being developed, and it is in the process yet. So yeah, I think in the coming months or years, we will see much more happening in this area. But thank you again, once again, for the wonderful discussion and presentation. And those who are watching us, I would like to request that please keep us following, and also give us feedback. How did you like it? And if you have more questions, of course, you can contact Giovanni via his LinkedIn, from his research profile that you can find. And in next week, we will bring another very interesting speaker. He will educate us about writing patents. He was my former team lead, and he's one of the top researcher from Sweden. He has highest number of patents in Sweden. So I think he will be a good source to educate us about this topic. So yeah, stay tuned, and we'll be in touch. Thank you.
Thank you.
Bye.